Okay, to wrap this up, we need to collect together general facts about any homomorphism between two groups. So the three things that you really need to know are laid out in Proposition 1 here. So let alpha from G to L be a homomorphism between groups. Then three things are true. First of all, alpha must send the identity of G to the identity of L. There's no choice. Secondly, alpha must send x inverse to the inverse of alpha x. Okay? So be careful here. This inverse is happening inside of G. This inverse is being done to alpha of x, which is happening inside of L. So the two inverses are happening here in different places. That's the inverse in G, that's the inverse in L. Likewise here, these two powers are happening in different places. This is alpha of x to the n, the x to the n computed in G. This is alpha of x being raised to the nth power. And this is true for any x in the group and any integer power that you like, even the negatives. Okay, so in short, homomorphisms must preserve identities, that's statement 1, inverses, that's statement 2, and integer powers, that is statement 3. Okay, so I'm going to walk you through the proofs of these because this is an incredibly important fact. Okay, so let's prove the first one first, that alpha has to preserve the identities in each group. So here we go. Let's just compute alpha of EG times alpha EG. Well, since alpha is a homomorphism, that is alpha of EG, but EG times EG is EG. Okay, so I have alpha of EG times alpha of EG is alpha of EG. Okay, now this is an equation in L, so there's no harm in me taking this and multiplying it by an identity on L on the right hand side. It doesn't change anything, so do that. So now you get alpha of EG times alpha of EG is equal to alpha of EG times the identity of L, which doesn't change anything at all. But that's an equation in L, so you left cancel the alpha EGs and you get alpha of EG is EL. So there you go. The homomorphism alpha has to preserve the identity in G and map it to the identity in L. Okay. For 2, what we're going to do is we're going to make use of the fact that inverses have to be unique inside of L. All right, inverses are unique in L. So we're going to prove that alpha of x inverse acts like the inverse to alpha x, and then by uniqueness, it must be the inverse to alpha x. But that's exactly the right-hand side. The right-hand side of this says the inverse to alpha x. So what we do is we just check it, right? So you take alpha of x inverse and multiply it by alpha x, and I'm going to show you this kills it off. So I'm going to get the identity here. And so you make use of the fact that alpha is a homomorphism to write this as alpha of x inverse x. But that's alpha of EG, but we just proved that has to be EL, right? So there you have it, and the same thing would work if I flip the order of these two. That's going to flip this into XX inverse, which is still the identity in G, which will still map to the identity in L. And so what you see is that alpha of x inverse kills off alpha of x on both sides. And so by uniqueness, this thing has to be the inverse of that. And so what I just said here is that this thing has to be the inverse of that. So alpha of x inverse is alpha of x inverted. And so therefore that proves statement 2, that the homomorphism alpha has to preserve inverses. Okay. For statement 3, that alpha also respects powers, we can just do it by induction, and it's not that bad. So note that this statement here is trivially okay when n is 0, because you get alpha of the identity is the identity. That's what the 0th power means after all. And we've already proved that. So here the 0th power would be EG. Over here it would be EL, and that would say that alpha of EG is EL, and it is. We just proved that. This is trivially true when n is 1, because it says that alpha of x equals alpha of x. Well, that's true. Now, what about the n equals 2 case? Here, we're going to start inducting here. Well, for the n equals 2 case, you have alpha of x squared, okay, alpha of x squared, that's alpha xx, but that's equal to alpha x times alpha x, because alpha is a homomorphism, and this is alpha of x squared. So there you have it. Alpha of x squared is alpha of x being squared. And then you can induct upwards and get it for all the positive integers. So it's not hard to go from here to alpha of x cubed is alpha of x cubed, and so forth. But we still got to get the negative. So when I start here and I induct upward, I get that this is true. I get that, that statement 3 is true for all the positive integers. I still got to get it for the negatives. And I can get that by inducting downward, right? So for instance, You already believe it when alpha is -1 because we just proved it. Alpha of x to the minus first is alpha of x to the minus first. But why is it true for -2? Well, because alpha of x to the minus second is alpha of x to the minus first, x to the minus first, right? But once again, you use the fact that alpha is a homomorphism, and that's alpha of x inverse times alpha of x inverse. But we've already proven that alpha preserves the inverse. That's alpha of x inverse times alpha of x inverse. And look at that. That is alpha of x to the second power, negative second power. So you get alpha of x to the minus second is equal to alpha of x to the minus second. And then you induct that way, but then you get the same thing for -3, -4, -5, and so on. And so when you carry forward the induction, you get it for all the negatives too. So it's true for all positives by inducting upwards. It's true for all the negatives by inducting downwards, and so it's true everywhere. Okay? So a good thing to do is for you to go back and revisit all of the previous 8 examples that I gave you and make sure that you see that the given homomorphisms actually do obey all these properties. Okay? So review all that, see if it makes sense, and then we'll go on to the next topic next. See you in a bit.